So hello again. This is another video. This is on another problem that I've been doing. So this is going to be suitable for anyone doing BEng honours degree or HNC or HND, I think. Basic structural behaviour again, mechanics of solids sometimes known as. This is to do with section properties, moments of inertia. So this one, I'm uploading this video now because I'd already started this and I thought this would be useful as well because, again, I can't find any other good videos on this. So basically we got a cross section here. This one's about glulam beams. So the question says, the cross-sectional dimension of an I-beam, which is made from 3 timber boards glued together, is shown below in this figure, as I've drawn out again. This beam is 6 meters long, simply supported at the ends and loaded with a concentrated load of 16 kilonewtons at a distance of 4 meters from the left-hand support. So this is another this is a moments of inertia question, but it's also simply supported analysis again. So I'm going to put this with the other simply supported videos that I've done. So the section looks like this. We got basically it's three timber boards glued together. So there's one at the top, it's 150 millimeters wide by 20 millimeters thick. Then we got this one here, which is 20 millimeters thick times 200 deep. And then number 3 is 20 millimeters thick times 250 wide. So it's a little bit wider at the bottom, so it's not symmetrical, this section, and it's glued together. So it's glued where the web meets the flanges, here, and here. So I think there's 4 lines of glue that run along the section. So all the dimensions in here. I might try and add this this written. I don't know if I can add this to the description of the video, but I'll try and do that so people can download it maybe. So I've drawn out the beam. We're going to need that later on anyway, so it's simply supported between point RA and B, and the point load on it 16 kilonewtons at a distance of 4 from the left hand support. So conventionally, I think it works out that A is equal to 4 meters, and that means because L is 6, B is equal to 2 meters. So basically that is just setting up the question for the solutions. This one, for the exam technique, we got I think it was 20 marks again, so that works out as 36 minutes, so just sort of almost 40 minutes, but we've got to try and fit everything in within 36 minutes. So the first part of the question says, part A, which is 3 marks, that's 5.4 minutes. What is the absolute maximum shear force in the beam due to the applied load? So to start off with, we need to do analysis of the simply supported beam. And actually, I read ahead. So the next part of one of the parts of the question is we're going to need the moments as well. So I might as well do that. I might as well work that out at the same time. So basically, I've drawn out, for the force diagrams, I just drew it out again so you can see it very clearly. You've got support A, support B, simply supported beam, spanning 6 meters, that's 4 plus 2. And then there's 4 meters on this side. And then you've got the point load of 16 kilonewtons, and then there's 2 meters on this side. In this question, there's nothing about factored loads or anything like that. They're just saying it's 16 kilonewtons, so we don't need to worry about doing factors and load factors or factors of safety. So here's the bending moment diagram, and here's the shear diagram. And the way I got that was basically, the first thing to do is as I've done on the previous video, just use simple overall equilibrium of the beam. So all the first equation you got, that gives you 3 equations you can use. So the first one is vertical well, actually, sorry, the first one is horizontal equilibrium, but we haven't got any horizontal forces, so we skip straight onto the vertical forces. So we say the forces up must equal the forces down, so that means that RA plus RB equals 16. So we're allowed to, I think from this thing we're allowed to use common sense, and we know that RA and RB are both going upwards because the load is going downwards. This is proved when we take moments. So the next thing to do is to take moments about, well, I've done it here. I've taken moments about point C. Oh yeah, that's just to verify RA equals RB. That's just to verify that RA plus RB is 16. So what you can do, actually, not the best way that I've done this actually. Usually it would be to take moments about A. We would do 16 times 4, which is 64. That would be clockwise, and then that would be 64, and that would be equal to 6 RB. Then that means that RB is equal to 64 divided by 6, and that is equal to that's obviously equal to 3672. It's, well, from below I know it's 5.333, because we basically, the other way to do it is to, if we take moments about point C, then we got RA times 4 equals to RB times 2, so that means that RA equals half RB, or obviously 2RA equals RB, so RB times half equals to RA. Then we substitute that back into equation, the vertical reaction equation, and we got half RB plus RB equals 16. So 1.5 RB equals 16. That means RB equals 10.66667 kilonewtons, and RA is 5.333 kilonewtons. So actually I think I'm going to do another video showing you how to do this a different way, because I've not done it conventional. Conventional way would be just to take moments about A. If you take moments about A, you would say, as I said, 16 times 4 clockwise is equal to RB times 6. So then 64 equals 6 RB. So RB equals 64 over 6. Sorry, so that is actually, it's 10, isn't it? 10.33. Because it's 10 and 4 over 6, which is 10 and 2/3, which is 10.66667. So sorry, so if you take moments about A, 16 times 4 clockwise equals to RB times 6. So 64 equals 6 RB. RB equals 64 over 6. That means RB equals 10 and 4 over 6, which is 10, 2 over 3, which is 10.6667. To find, so then you got RB equals 10.6667, and we know that RA plus RB equals 16, so that means RA must be 16 minus 10.666 equals 5.333. So basically I've done that, and I've checked it by taking moments about C, but I should have done it the other way around. So that means so we found the maximum shear because the maximum applied shear is 10.66, and that's RB between beam length 4 and 2. Maximum shear is 10.66, and then on that side it's 5.333. And that is because the load is not on the centre of the beam. If the point load was in the middle, it would just be 8 on either side, obviously, wouldn't it? So because it's a little bit closer to RB is bigger, so there's a bigger shear on this side. It's really simple stuff. So what we need to do as well, in the next part of the question, we need to find the maximum moment. So I'll just do that now as well, because we've got the diagrams in front of us. So if we take moments about the left hand side of C, we've got RA times 4 is the moment applied at C. So that is 5.333 times 4 meters, and that is 21.333 kilonewton meters. So that's there we got our first 3 marks is done, because part A says what's the maximum shear. Maximum shear is 10.6667. So the next part of the question, this is a little bit more complicated. Not to D, this is the moment of inertia section of the question. It says determine the position of the neutral axis of the beam section about the x-axis. So go back to diagram 3. Basically, well, this is the same as diagram 3 here. We use the following notation. So AS is the area of the individual section components of the beam. So basically that's the area of each rectangle. X bar, we call that the distance from the center of the area of the section considered to the x-axis, and X bar SB, I've said the distance from the center of the section of the rectangle as whole to the x-axis. And then so the distance to the neutral axis is, that's what X bar SB is. The distance to the neutral axis is X bar SB. That equals to the sum of X bar times AS divided by the sum of AS. That's the equation that you need to know. So that's basically, it's just the x-axis is at the bottom of the section here. So there's a horizontal line, the bottom of the section. Area of each section is just like the area of the rectangle. So it's just B times D, and that's going to be B times D again. But obviously on B is only 20 on this one, 150, and then B is 250. So now, so on section 1, the area of the section is 150 times 20. That's 150 wide times 20. That's 3,000. So that's the first part of the X bar. That's AS. So basically, X bar is the distance from the x-axis to the center of area of the rectangle we're looking at. We're looking at rectangle 1. So the center is 20 plus 240 plus 20 over 2. That's 20 over, I've written it the other way around, but it's 20 over 2 plus 200 plus 20. So that's 230. So X bar A, which is the top part of this equation that we're trying to find the sum of all those parts, that's equal to 230 times 3,000. So that's equal to 200 times 3,000 plus 30 times 3,000. That's equal to 6,000 times 100 plus 9,000 times 10, which is 600,000 plus 90,000, which is 690,000 millimeters cubed. Then for section A, we got, for section 2, which I've called this is the vertical part, the vertical section, the web, section 2. Yeah, so basically section 1 was the top flange. Section 2 is the web. So AS is equal to B, which is 20, times 200, which is 4,000. X bar is the distance to the center of the rectangle from the bottom, very bottom, so it's 20 plus 100 over 2. 200 over 2 plus 20, 120 millimeters. So AS times x bar, which is this again, is 120 times 4,000, which is 100 times 4,000 plus 20 times 4,000 equals 400,000 plus 80,000, 480,000. Just for me, I just think it's so easy to work these out just without a calculator, because if you just break it up into 2 parts, it's just as quick as using a calculator, I find. And then final is section 3, that's the bottom flange. And that is equal to, so the area of that section is obviously 20 thick times 250, which is 5,000 millimeters squared. And the x bar, that's the distance from the x-axis at the bottom to the middle of the center of area of this, is 20 over 2. So that's 10. So AS x bar, which is this top part of this equation again, is equal to 5,000 times 10, and that's obviously 50,000. So to find, now we've found all the values, we've got all the area values, we've got the area values over 3 sections, we've got the x bar, that's the average, that's the x distance of each piece from the x-axis. All we've got to do now is we make a table out for the 3 parts. So we got section 1, x bar equals 230, as I said, that was 20 plus 200 plus 20 over 2, which is 230. Section 2 was 20 plus 100. Section 3 is 10. AS has calculated 3,000, 4,000, 5,000. And then X bar times A, 690,000, 480,000, 50,000. And then, so in the equation, we just add those up now. We need the sum of X bar AS and the sum of AS. So the sum of AS is 12,000. 3,000 plus 4,000 is 7,000 plus 5,000 is 12,000. 690,000 plus 480,000 plus 50,000. That is equal to, obviously, 9 plus 8 plus 5 is 22. And then 6 plus 4 plus 6 plus 4 is 6 plus 4 is 600,000 plus 400,000 is 1,000,000, so it's 1,220,000 millimeters cubed, because it's 90,000 plus 80,000 plus 50,000, that's 170,000, 220,000, so it's 1,220,000 millimeters to the power of 3. So personally, I don't think you need a calculator to do this question, because it's just as easy. So then, to find the distance to the neutral axis, x bar, it's just 1.22 times 10 to the power of 6, which is that number, divided by 1.2 times 10 to the power of 4, which is the area. So it's x bar times A divided by, that should be x bar times AS divided by AS. That gives you 101.67. So that's another 3 minutes. I think that's another, that's another 3 marks. So you get 5 minutes to do that. 5.4 minutes, I think it is. So I'm going to split this video into 3 parts. The next part of this question is to find the second moment of area of the question section about the vertical axis. So I'll do that next, but please like the video, subscribe. I try and add this text to the link so then you could download it as well. Very simple stuff. Hopefully you're understanding. Any questions, please post in the comments. Thanks.